Hi, my name is Eric, a computer scientist living in Charlottesville, Virginia. It was 3 a.m. and I hadn't slept for 48 hours in order to finish a project on time. A few hours later, I woke up at 7 a.m. after 4 hours of sleep and walked to my workplace. Suddenly, pain occurred in my left chest. Then, I fell on the ground and nearly lost consciousness. During coma, I heard someone call 911. After a few minutes, I heard the sound of an ambulance. Some medical workers came and took care of me. Luckily, I live in Charlottesville and the hospital is close, so the ambulance came quickly, so I got saved. Also, I'm young and my heart is strong. But what if I live in a rural area that doesn't have a hospital nearby, or I'm old? Can I survive until ambulance comes and saves me? So, I did some research online. First, I want to know, why does the EMS response time matter? According to an article of Journal of the American Heart Association, shorter EMS response time means higher probability of survival. Even 1 second can determine life or death. In order to know more, me and my friends decided to use a clustering model to analyze disparities in EMS response time. The first step is to gain data. Thanks to the National Emergency Medical Service Information System, we gained 2017's NEMSIS public release research dataset and use it to train our model.
To analyze our data, we developed a Python project on Google Colab to perform k-means clustering on a dataset consisting of 7 million samples. Due to time constraints, we focused on a subset of only 100,000 samples. To determine the optimal number of clusters, we constructed an elbow plot. Examining it, a sharp dropout slowed down at k equals 6, suggesting that 6 clusters would yield the most effective results. Subsequently, we computed the cluster centroids and predicted the average values of each cluster alongside their respective feature names for further analysis. Here's a glimpse of the centroid values for clusters 0 and 1.
Using k-means clustering with 6 clusters on EMS incident data across Virginia, we identified clear patterns in EMS response-related features. Among the features analyzed, EMS system response time and scene response time exhibited the greatest variation across clusters, with mean values around 21.67 and 23.46 minutes. These features also showed presence of outliers in a wide range, indicating significant differences in EMS response efficiency among the clusters. Other time-related features such as EMS shed time, about 2.08 minutes, and dispatch center time, approximately 2.37 seconds, and transport time, around 1.75 minutes, showed less variation but still contributed to the distinguishing clusters. The variability in these operational times suggests differences in EMS workflow and resource utilization across the clusters. The clustering results reflect heterogeneous EMS performance characteristics, with some clusters showing notably higher response and transport times, which could correspond to areas with limited EMS resources or logistical challenges. The presence of outliers and key features like response and shut times highlight some potential delays in certain EMS incidents that warrant further investigation. In conclusion, the k-means clustering analysis reveals distinct groups of EMS incidents characterized by varying response and operational times across Virginia. The differences in cluster centroids suggest disparities in EMS resource allocation and efficiency, with some clusters experiencing longer response and transport durations. These findings underscore the importance of targeted strategies to optimize EMS deployment and reduce critical delays. By leveraging these cluster insights, policymakers and EMS administrators can better allocate resources to improve emergency response outcomes statewide.